Hello class, welcome back. Today I'm going to be talking about chapter 4. Chapter 4 we're going to be going over gravity, projectiles, and satellites. And just to let you know, you do have your first test this week. And test 1 is going to cover chapters 1, 2, and 4. 1, 2, and 4. Right? And so there is a review on Blackboard. Under the week 2 tab, there's going to be a test 1 review. You can go ahead and pull that up, take a look at it, try to run through the review, see how much you can do, see what you do or don't understand, and then I will be posting a video either tomorrow, maybe even sometime today, most likely tomorrow, basically of me going over the review, going through each answer and explaining why the answer is what it is, and just basically trying to explain it as in-depth as possible, just so that you can have a full understanding of the review and everything that's on it, and so that you can be prepared for your test. All right. Yeah, so now let's go ahead and get started with chapter 4. So chapter 4, we're going to start with basically the universal law of gravity. And so it's basically Newton's universal law of gravity. So it's Newton's law of universal gravity, I should say. Newton's law of universal gravity or gravitation. As you may know, the old story of Newton as a child sitting under an apple tree, and as Newton was sitting under this apple tree, an apple falls down, hits him on the head, and then he begins to wonder, well, why does the apple fall downwards instead of upwards? Now, Isaac Newton was not the one to discover gravity, but he was the one to discover that gravity is universal, because before Isaac Newton, we never really connected the fact that things fall towards Earth with, things like the stars or the moon going around the Earth, things basically outside of Earth. We never connected gravity with things that were happening outside of Earth. But it comes to find out that basically those two things are one and the same. So the same thing that pulls the apple down to the ground is the same thing that caused the moon to go around the Earth, which is the same thing that causes the Earth to go around the sun, which is the same thing that causes the sun to go around the center of our galaxy, and so on and so on. So basically, Newton's law of universal gravitation says that every body in the universe, basically every piece of matter that's in the universe, attracts every other body or every other matter that's in the universe with a mutual force, right? So basically that just means if some matter is here and if I have another marker, and some matter here, right? So basically these two masses are attracting each other through the gravitational force. But we see here that these two things aren't gonna slam together, because gravity doesn't affect things that have, a small mass. And we're gonna see why that is when I write out the equation here. So if I were to write out the equation for Newton's law of universal gravity, so I'm just gonna erase this. So Newton's law of universal gravity is basically a force. It's a force that's given by a capital G, which is just some constant or just some number, times mass 1 times mass 2, which is the two masses that are being attracted towards each other, divided by the distance between them for d squared. So this right here is basically what's keeping our whole solar system, galaxy, universe kind of held together. This right here is what's keeping the planets in orbit. This right here is what's keeping the moon in orbit, you know, all that good stuff. This right here is what's keeping you stuck to the ground instead of flying off the earth. This is what's causing things to fall downwards towards the ground, satellites in orbit, all that. And so let me just write what G is. Let's see. Well, we'll get to G a little bit later. But let me see if I could describe this equation to you. So let's go with the moon. Well, this is the moon here, and say this is the Earth here. All right. And so if you want to find the gravitational force between the moon and the Earth, because we know basically the moon is pulling on the Earth, right? So there's basically a force this way. There's a force that way from the moon pulling on the Earth. Then there's also a force pulling on the moon from the Earth. So basically the moon is causing this force. Maybe let's see if I can color code this. Let's make the moon red. Boom. So the Earth here is pulling on the moon with this blue vector or arrow or force. And then the moon is also pulling on the Earth with this vector here. All right, and so this distance d this is distance d, which is the distance, let's see if you can see that, which is the distance that's between the Earth and the moon. And let's say Earth has mass m1, and the moon has mass m2. So if we want to find what this force is, because we know both of these forces are equal and opposite, because as I mentioned in the last video, for every one interaction, there is two forces that act in equal opposite directions. So these forces have the same, basically, length, but they're being pulled in equal opposite directions. So this force right here between the Earth and the moon is given by this equation. So if you want to figure out what that force is, we'll use this equation here. We'll take the mass of the Earth, mass of the moon, plug them in there, take the distance between the Earth and the moon, put that on the bottom and square it, and then multiply that by this gravitational constant, G, which again is just some given number that would be given to you. Right? So now let me ask you this. Which one is pulling on each other stronger? So like, is the moon pulling on the Earth stronger, or is the Earth pulling on the moon stronger? Right? Well, they actually pull or attract each other with the same force, right? Because these forces are equal and opposite. Now also notice that if the moon were to move further away, so say the moon is not here, but now I move it further away. Let's say I move it further away, so like over here. So now the moon's new distance is, put it in a different color. Let's do black here. So now the moon's distance is this here. So if you increase the distance of the moon from the Earth, what do you think will happen to the gravitational force between the Earth and the moon? Right? Well, the gravitational force is actually going to get smaller, right? So if we have these two objects here, and then there's some gravitational force on them, you know, pulling, one pulling this way and one pulling this way, one pulling that way. If we pull these things apart, make them further, then the gravitational force between them gets less and less. And so how much smaller does it get with the distance is the question. Well, it decreases with the inverse square. See how this d is squared here and it's on the bottom? This is what we call the inverse square. So assuming the masses were to stay constant, we can write this equation this way. Boom. So basically, this means that everything else in the equation, like this gravity and these two masses, are basically constant. So we're not really worried about G or the masses right now. If we were to look at force and compare it with the distance between the masses, we see that basically force is inversely, when I say inversely, I mean that the D is on the bottom and it's squared. And so force follows an inverse square law. All right, so let me show you how that looks on a graph. So if I were to draw a graph here, where this bottom part is the distance, and let's say up here is the force. So if two objects are really, really close to each other, is the force going to be greater or lesser? Well, the force is going to be greater, right? Because these two objects are very, very close. So the force is going to be really, really high. So like up here somewhere. Then the distance is really, really small. So it's going to be somewhere towards, you know, here. You know, the distance is small, but the force is going to be high way up here. Now, let's say it's this far apart, you know, really, really, really far apart. So the distance is way out here. Then the force between these two objects is going to be way less, right? So down here somewhere. So like around here somewhere, boom. So now as you get further and further, this graph is going to look like this, like that. So this is what we call the inverse square graph, meaning that as you get closer and closer, or as your distance decreases this way, your force is going to increase. See that? Or vice versa, you know, the further and further you get away, so the further and further you get away, your force is going to go down and decrease. But it's never actually going to be zero. Notice that. Notice it's never really going to be zero. It's just going to get real, real close to the bottom. But it's never going to hit zero. It's just going to get smaller and smaller and smaller and smaller, but never going to be zero. That basically means no matter how far apart two objects are, there's always going to be, so no matter how far apart two objects are, it's always going to be some very, very, very small amount of force of attraction between those two objects. And so this is why basically force is affecting everything in our, you know, solar system or galaxy or universe, because no matter how far two masses are, they're always going to attract each other, you know, by just some small, teeny tiny amount if they're really, really far. All right. So let's see, just looking through the slides here. All right, so now instead of looking at the distance, let's look at if we change the masses. So let's say now, let's go back to the Earth-Moon situation. So we've got the Earth here and the Moon here. And this is some distance d between them. All right, so now let's say we keep this distance d between them the same, but let's now say we increase the mass of the Moon. What's gonna happen to the force between the Moon and the Earth now? So if we increase the mass of the Moon to, say, something like this, so we increased the mass. So if we increase this mass here, or if we increase M2, and we say M2 is for the Moon, M2 and M1 is for the Earth, then what's going to happen to the force of gravity between these two? Well, the force of gravity is going to increase, right? Because if we increase this M on the top, keeping this M over here, the Earth, the same, then that's just going to make the overall force bigger. So if we increase the mass of something, then the gravitational force between those two objects is also going to increase. And same vice versa, if I were to decrease the mass to something teeny tiny, then the force between these two would decrease. All right, so I think that makes sense, right? All right. Boom, just looking through the slides. Let's see. Okay. So now let's say, looking at slide 16 here, let's say, slide 16, they asked the question, if the masses of two planets are somehow doubled, the force of gravity between them is what? So we got some mass here, this planet and this planet. They both have some mass, M. Let's say they both have the same mass. They both have the same mass. So the force of gravity, I'm just erase these subscripts, is going to be given by this equation, right? So we can actually write that as, because both of these masses are the same, it's going to become m squared. Now, if we were to double both of these masses, so this becomes 2m and this becomes 2m, then how is that gonna change the force of gravity between the two? Well, now, if I were to use 2m and 2m in our force of gravity equation, we would get the force of gravity equals G. And so now it's 2m times 2m, so now it's going to be 4m squared divided by the distance squared. We kept the distance the same. So notice how everything here is basically the same as here, except now there's a 4 on the top. So basically that just means the force is going to be quadrupled, or it's going to be 4 times as big if you increase the mass of both objects. Right? Well, let's say I just doubled the mass for one of the objects. So this one stayed the same, but now this one's 2m. Well, then the force, instead of being quadrupled, is going to be what? Well, it's just going to be a 2 now there. So now here it's going to be doubled because now it's a 2 here while everything else is the same. And so now let's say this mass is cut in half. It's cut in half. Now how is that going to change this? Well, you're right. It's just going to put a half on there. So now the force of gravity between these two masses is just going to be half of what it originally was. So I think that makes sense. Increase the mass, you increase the force. If you decrease the mass, then you decrease the force. All right, so now let's talk about this gravitational constant G real quickly. We know that the gravitational constant G is given by this value here, 6.67 times 10 to the negative 11. And these are the units for that constant. Don't really worry about that, some crazy units, so don't stress too much about that. But just notice how this constant is really, really small. It's times 10 to the negative 11. That basically means it has 10 zeros in front of it. So if I were to write that out, it would actually be G is actually equal to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7. So this is the value of G, Newton meters squared, kilogram squared. Really, 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 really small, right? Really small. And so the fact that this is so small is why basically you aren't being pulled towards someone that's right next to you, right? Or why basically it's why, you know, these two objects here, even though they have some mass, if I set them both down, they're not being attracted towards each other. They're not actually moving towards each other because this gravitational constant G is so small. So let me show how that works. So let's say we got two people. So we got a person right here, and we got a person right here. And since both of these people have some mass associated with them, according to Newton's law of gravitation, these two people should be attracted to each other by this force here, right? Where this guy can be mass 1 and this person be mass 2. So let's say person 1, let's say they both have the same mass. Let's say person 1 equals, let's say 50 kilograms. That's roughly about 100 pounds. Yeah, so let's say person 1 weighs 50 kilograms and person 2 also weighs 50 kilograms. And let's say their distance from each other, let's say, no, they're in the same room. So let's say the distance is 2 meters. What is going to be their gravitational attraction towards each other? Well, we'll just use this equation right here, right? So using this for mass 1, this for mass 2, this for the distance, and then this small number, G, to figure out what the force F is between them. So let's see, what's that going to be? My calculator. Well, the force between them is going to be 6.67 times 10 to the negative 11 for that, times both of those masses, so times 50 times 50, divided by the distance squared, so divided by 2 squared. That gives me, let me write it down here. That gives me a force of 0.000123 0.00042. Actually, I can write right here, 4, 2. Boom. And that's in newtons. So that's how small the force is between these two people. And so that's why you don't actually feel, you know, your attraction to other people, because it's so small. You know, so small that you don't even feel, you know, this small force. So now let's do Newton's law of gravitation for two massive objects, because that's where this equation really starts to show its effect, when things have a very high mass. So let me do this force of gravity between the Earth and the Moon. So between the Earth and the Moon, so all we need basically is the masses of the Earth and the Moon and the distance from the Earth to the Moon. So let me just look those up really quickly here. Okay, so the mass for the Moon, which I labeled as M2, is 7.3 times 10 to the 22 kilograms. Mass of the Earth is 6 times 10 to the 24 kilograms. And the distance between the Earth and the Moon is basically 384 times 10 to the 6 meters. Notice this is basically 7.3 with 21 zeros behind it. So the mass of the Moon is huge. The mass of the Earth is basically 6 with 24 zeros behind it. So also super huge. So now, using these here and our gravitational constant, what's the force between the Earth and the Moon going to be? Well, putting that in the calculator, we get 7.3 to the 22 times 6 to the 24 times 6.67 to the negative 11, and divided by 384.4 e to the 6 squared. Boom. So rounding this number, I get about, the force between the Earth and the Moon is 2 times 10 to the 20 newtons. Boom. So this number way different, way more massive, way bigger than, you know, the force of gravity between two people that's only 2 meters apart. So we see then basically this force of gravity, or this force, universal law of gravity, is really only effective for supermassive objects that are in space, so like stars, planets, you know, things of that nature. All right, so now, if you're looking at the PowerPoint, now we're going to talk a little bit about weight and weightlessness. Weight and weightlessness. So the best way to describe weight and weightlessness is the old elevator scenario. So let's say you're on an elevator, right? Boom, this is your elevator. And let's say there is a scale on this elevator. So I'm gonna make this right here the scale. So this outside box is your elevator, and that little red box there is your scale. So what does a scale do? Well, a scale basically tells you how much you weigh, right? And we know basically your weight is related to the gravitational force, you know, the force of gravity that's pulling on you downwards. So basically, if you weigh more, you have more weight, then the force of gravity acting on you is going to be basically more or heavier. So let's say this person weighs, let's say weighs, I don't know. Let's say he has a mass, actually. He has a mass of, let's say 10 kilograms. I don't know. So he has a mass of 10 kilograms. So his weight is going to be mass times gravity, right? That's going to be basically 10 times 10, because we know little g is roughly about 10 meters per second squared. So his weight is going to be 100 newtons. So now, if you're on this elevator and the elevator accelerates upwards, then how much is he gonna weigh? Well, he's gonna weigh a little bit more, right? Well, you've probably experienced this before when you're on an elevator and the elevator suddenly goes up. You kind of feel weighted downwards, right? You feel weighted downwards when the elevator goes upwards. And same vice versa, right? If you're on an elevator and the elevator goes downwards, you feel kind of lifted upwards. So if this elevator goes, if it goes upwards, if the elevator goes upwards, you're gonna appear to weigh more on this scale. You're gonna weigh more. So let's see, weigh more. But if this elevator goes downwards, then you're gonna appear to weigh less. Weigh, I spelled that right? I think so. Or it says weight more, weight, yeah, so weigh less. All right. So now, let me ask you this. How fast would this elevator have to accelerate downwards for you to basically feel weightless, or to be basically lifted off this elevator? Well, if this elevator were accelerating downwards with the same acceleration as gravity, would basically, so let me see if I could draw that out here. It'd basically appear to be weightless. So here, let's say this elevator is going down with some acceleration that's equal to gravity. And so basically the elevator is going down so fast that you basically lose contact with the ground, and you're just kind of floating in there, falling with the elevator at the exact same acceleration, right? Right? So basically, as the elevator is falling downwards, you're also falling downwards at the same acceleration as the elevator, so you're gonna feel to be weightless. So basically, the main idea you need to get from this is if you're on an elevator and the elevator goes up, you're gonna appear to weigh more. If the elevator goes downwards, you're gonna appear to weigh less, but you don't actually weigh less or more, right? You still have the same mass. You know, you didn't lose or pick up any mass while you're on this elevator. It's just what appears to be so because this elevator is accelerating up or downwards. And then if the elevator is accelerating downwards just as fast as gravity, then you will appear to be weightless, right? Okay, so next, now I'm going to talk about, if you're looking at the slides, I'm going to jump down to projectile motion. So now we're going to talk about projectile motion. So I'm going to write projectile, all right, motion. Now, basically, projectile motion is whenever, or it's basically any motion that goes in some kind of arc. So here's an example. Let's say you're on the ground and you kick a football, and the football's gonna go in some motion like that, right? So this is what we would call projectile motion. Another example would be, let's say you're on a cliff. So let's say you're on a cliff and you throw a rock off the cliff. That would also be projectile motion. All right. Boom. What's another example? Well, another example of projectile motion is, let's say you're just standing here, just standing there, and you throw a rock or a ball or some object upwards. No, so we know it's gonna go upwards, no, pause, and then fall back downwards. Boom. This right here is another example of projectile motion. So these are basically the three kind of main examples you need to think of whenever we talk about projectile motion. So we got this whole arcing situation here, which is kind of similar to you just throwing something up and coming straight down. And there's the throwing something off of a cliff, or shooting something off of a cliff scenario. And I guess also for this cliff scenario, it can look also like this. You can kind of throw something upwards, then it's going to basically fall downward. All right. But for the most part, these are the scenarios of projectile motion you just need to keep in mind. So by definition, projectile motion, according to the PowerPoint, is any object that moves through the air under the influence of gravity. So basically, in all these situations, something is being pulled downwards towards the ground because of gravity. All right. So another thing I want to stress about projectile motion is usually for projectile motion, there is some basically movement in two different directions. So there's basically movement in two directions. But there's only acceleration in one direction. Right? And what direction do you think that acceleration is going to be in? That's right. So we know basically the acceleration is always going to be downwards in the y direction. So acceleration is downwards in y direction. Right, and this right here is basically because of gravity, right? Because gravity is basically pulling all things down towards the ground. So acceleration is always going to be downwards in the y direction. And so for the x direction, the velocity is always going to be constant. So velocity in x direction is constant. All right, so in projectile motion, acceleration is always downwards in the x direction, or in the y direction, I mean, and the x direction always has a constant velocity. So in the y direction, the velocity is changing, or it's accelerating downwards, and in the x direction, the velocity is going to be constant. So let me show you what I mean by that. All right, so let's do this problem. Something's moving in this kind of motion, right? So something's moving in this kind of motion, right? So I can basically draw the vector for acceleration, because it's going to be downwards at every point on this graph, or on this path, right? Actually, better yet, let me draw it like this. So let's say you kick a ball, and the ball has basically this velocity here. Boom. In that direction. So this velocity has, we call it a component. So it has a y part and it has a x part. So it has this arrow here basically represents how fast it's going in the x direction, right? And let me use a different color. Let's use black for the y. So this black arrow represents the velocity that's upwards, right? Because you kick it at this angle, or you throw it at this angle, and so basically a velocity in the x direction and a velocity upwards in the y direction. So let's say I go to this point here. Now, what's the velocity going to be in the y direction? Well, let me just draw it out here. It's actually going to be a little bit less. It's going to be a little smaller. Because as something goes upwards, it actually slows down, right? Because it's being pulled downwards by gravity. And then there's this, the velocity in the x direction, which is actually going to remain constant. Boom, like that. And so now what do you think about the top of the path? So let's say at the very top of the path right here, then how are these velocity vectors going to look for the x and y direction? Well, at the top of the path, we know whenever we throw something upwards, at the very top of the path, it pauses for a second as far as the y direction is concerned. So it actually won't be any arrow upwards at all. But the velocity in the x direction, that's still going to be there because it's constant. So it has the same velocity this way still. And now, let's say I go right here. Well, now this object is falling downwards, right? So now it's falling downwards. And it still has that same velocity in the x direction. Now what about here? Well, it's still falling downwards, but now it's falling even faster, right? Because gravity is accelerating it downwards. And it still has the same velocity in the y direction. Then once it gets here, right before it hits the ground, it has this same velocity that it had upwards, but now it's downwards. It still has the same velocity in the x direction. This is right before it hits the ground. Boom. So now let me restate what I said a moment ago. So notice how the velocity in the x direction is basically constant. See, that velocity is constant. So it's not accelerating in the x direction. The velocity is constant because there's no forces, basically. There's no forces in the x direction. The only force is the force of gravity pulling it downwards. So basically, as this object goes up, it slows down, slows down until it gets to the top. And then it basically has no more velocity in the y direction. And then it starts to fall downwards, increasing velocity downwards. And so right before it falls, it's going to have this same velocity that it initially started with, but now it's downwards, while the velocity in the x direction stayed the same the whole time. So I hope that made sense. Let me see, let me check the PowerPoint. Okay. So now let me show you two extreme cases that may help you, that may kind of blow your mind a little bit. So let's say, because we know basically if we drop two objects from the same height, they both fall and hit the ground at the same time, right? So now let's say you're standing here, all right? And let's say you have two objects in your hand. You have, let's say you have a water gun. It's supposed to be a water gun, and you have a rock in this hand. All right? So let's say you squirt the water gun and you drop this object at the same time. So now my question to you is, which hits the ground first, the water or that rock that you drop? Right, so we know basically this water is gonna go, it's gonna do something like this. Boom. And we know this rock basically is at the same height, it's supposed to be at the same height there. It's just gonna fall downwards like this. So now, a question to you is the water or is the rock here gonna hit the ground first? Well, since both of these objects started at the same height, then they're both actually gonna hit the ground at the same time. The only difference from these two scenarios is the water has some velocity in the x direction. So it has some velocity in this direction. So let's say I would draw that velocity here, in that direction, here, in that direction. So that velocity in the x direction stays the same. Now let me draw the velocity for the downwards direction, right? For the y direction. Because so right here, it's not falling yet, but then right here, it starts to pick up a little speed. And then here, it starts falling a little bit more. Then here, it starts falling a bit more. Then here, even more. Until it hits the ground. Well, the same thing is going to happen for this rock. It's supposed to be at the same height there. It's supposed to be at the same height. So this rock's going to just start there. Then it's going to, so let's say right here, it's going a little faster. And then right here, it's going a little faster. And then right here, it's falling a little faster. Boom. Boom. So notice basically the velocity downwards here is going to be the same as this velocity downwards there. This velocity downwards here is going to be the same as this velocity downwards here. Right? So I hope that makes sense. This is something you can probably actually try at home if you have a water gun. You know, just kind of hold both of them level and drop or squirt the water gun and drop the object at the same time. The only reason they may not fall at the exact same time is because of air resistance. Basically, the air resistance may prevent the water from falling at the maximum speed that it could fall at. And so this object may appear to really hit the ground first, but if you were in a situation where there's no air, then this would definitely be the case where they fall at the same time. Even if you try it at home, they still should roughly fall around the same time, right? So I hope that makes sense. Let's see what's next. So basically, again, just want to mention both of these objects have the same acceleration downwards. All right, so now let's talk about satellites. So satellites. Basically, a satellite is anything that is orbiting around our planet Earth. So the moon would be considered a satellite. And basically, of course, other satellite dishes that we have, orbiting around our Earth for telecommunications, for internet, for GPS, all those kind of things are, of course, satellites. But by definition, a satellite is anything that is just orbiting around the Earth. So now let's say, let's talk about what it takes to basically orbit around the Earth. So let's say this is the Earth here. And let's say you're on top of a mountain. So here's some mountain. That's the mountain. All right. And you're standing on top of this mountain right here. That's you. And let's say, you throw an object, right? Kind of go back to projectile motion. If you throw an object off of this mountain, an object is going to go like that. Let's say you throw it even harder. If you throw that object even harder, then it's going to land basically a little bit further, right? Boom, kind of like that. Well, let's say you have, Superman strength, and you can actually throw this object so hard. You can throw this object so hard that basically it will go so fast that it can actually revolve all the way around the Earth. So this basically is me. So let's say you throw it this hard, throw it a little harder, throw it a little harder, but you can actually throw it so fast that it orbits all the way around the Earth and comes back towards you. So basically, you can throw an object so fast that it basically outruns kind of how fast it's falling downwards. So now let me quickly talk about elliptical orbits. So let me just erase this. Talk about elliptical orbits. And basically, an elliptical orbit is anything that orbits in not a circle, but a more oval-like path. So let's say this is the sun here. That's the sun. So let's say there is a comet that orbits around the sun, and it goes in some path like this. So this comet would actually be in some elliptical path because it goes in a oval, versus for the Earth-Moon situation where this is the Earth and we have the Moon that orbits around it in basically a perfect circle. So this is Earth-Moon. Sorry about my handwriting. That's supposed to say Earth. I'll try that again. Earth, Moon, and this is Sun, Comet. So for the Earth-Moon situation, we see basically this orbit is circular motion. And whenever an orbit is in circular motion, the velocity of that object in orbit is going to be constant. So here, velocity is constant. So basically, if I drew this arrow as the velocity, this arrow as the velocity, this arrow as the velocity, that arrow as the velocity is basically constant as the moon goes around the Earth. Now for this comet, the velocity is not going to be constant. So let me actually draw out how the velocity is going to behave here. So, right here, the velocity is going to be this way in some direction. Velocity here. Velocity here. Velocity here. Boom. So basically, for anything in an elliptical orbit, the velocity is going to vary depending on how close that object or this comet is to the sun. So when that object is very, very far away from the sun, its velocity is not going to be that fast. Then as it gets closer and closer, it's going to start moving faster and faster, so the velocity is a little bit bigger here. Then as it kind of wraps around here, and when it's close as possible to the sun, it's going to have its maximum velocity. So right here, it's going to be moving really, really, really fast. And then it's going to kind of shoot around and then slow down and slow down and slow down until it has its least velocity. So if I were to replicate the motion with my finger, it'd be slow, speed up, speed up, speed up, speed up, go zoom, and then kind of swing around, and then slow down, slow down, slow down, slow down. And then once it passes this point again, it'll again pick up, swing around, over and over. So, why is it that it actually moves faster when it's closer and moves slower when it's further away? Well, the reason is because of Newton's law of universal gravity. So it's basically because of this equation here. D squared. It's basically because of this equation here. Because as two objects get closer to each other, the force is going to be greater. So the closer two objects are, or two masses are, the greater the force. And that increase of force is basically what causes it to speed up around when it's really, really close, and then slow down when it's further away. Versus for a perfect circle, the distance here, this distance d, is the same all the way around. So for the moon doesn't actually speed up as it goes around the Earth. It just kind of goes around the Earth in its same, 27, 28-ish days. So it takes basically 28 days for the moon to go around to get back to this point. And it continues to take roughly about 28 days to go from here to all the way back around. Okay, so now the last thing I'm going to talk about is going to be escape speed. Escape speed. So going back to the scenario of you standing on some mountain on Earth. Well, this is Earth, there's some mountain, and you're standing up here. You're standing up there, and you throw an object off of this mountain. So you throw an object off of this mountain, and let's say you throw it at, you throw it at the 8 kilometers per second. So if we throw it at this speed here, it's basically going to go all the way around the Earth. Boom, like that, right? But what if you throw it even faster than that? What's going to happen then? Well, if you throw it even faster than that, then that object is, let's say, ignoring that, if we throw it even faster, then that object is going to travel in more of an ellipse. I don't know if you can see that down there. Kind of like that. And then you can even throw it so fast that it actually escapes or outruns the gravitational field of the Earth. So you can throw it so fast that it just leaves the gravitational field or outruns the gravitational field of Earth. So here, when it's in the ellipse, in the elliptical path, or even when it goes in the circular path, basically the gravitational field of the Earth is strong enough to keep that object within its orbit. Even if you throw it a little bit harder and it makes the elliptical or oval path, the gravitational field of the Earth kind of still keep it within range. But you can also throw it so fast that it actually leaves or outruns gravitational field of the Earth altogether. It doesn't actually leave the gravitational field, because we know Earth's gravitational field, basically it pervades everywhere in space. Remember how I said with the graph here, how it basically never really hits zero, it just gets really, really close, where that's the distance and this is the force of gravity here. So because it never really reaches zero, this object will never actually get outside of the gravitational field of the Earth, but it can get so far to where the gravitational force of the Earth is so little that it doesn't matter. So this is what we mean by an object outrunning the gravitational field of the Earth. But it doesn't actually leave it just kind of outruns it. All right, so now I just want to talk about a few of the problems that you're going to see in the Mastering Physics homework. And one of those problems deals with projectile motion and kinematic equations. And so kinematic, it's a different marker. Kinematic equations. Kinematic equations. And basically use this set of kinematic equations that I'm about to write out here whenever the acceleration is constant. All right, so this here is the set of kinematic equations where basically this equation can tell you the distance of an object if you know the initial velocity of the object, how long that object has been accelerating. So if you know the initial velocity, the time, and the acceleration of that object, you can figure out how far it went. You can find the final velocity of an object if you know the initial velocity, plus knowing its acceleration and knowing how long it was accelerating. And you can also find the final velocity of an object if you know its initial velocity, plus 2 times the acceleration and the distance traveled by that object. Right, so we can only use these equations when acceleration is constant. So whenever the acceleration is constant, you can use basically this set of kinematic equations. All right, so whenever an object is in free fall, the acceleration is constant because it's being pulled down due to gravity. So whenever an object is in free fall, we can use basically this set of equations here, right? So in the Mastering Physics homework, they give you a scenario, well, they actually demonstrate it to you, where you have some track here and some cart, and this cart has a ball on it. And then this cart is attached to some mass over here. And so this mass is let go, it falls downwards. So this mass falls downwards and then pulls that cart to the right. And then as that cart goes to the right, it shoots the ball upwards. it shoots the ball upwards while the ball is still being continued to be pulled towards the right. And we see basically this ball is going to go in some motion like this and land right behind the cart. Right? So let me try to explain this a little bit. I think he explains it pretty well in the video, but just to remind you, so this cart basically is attached to this mass. This mass is falling down with free fall, so this mass is accelerating downwards. So since this mass is accelerating downwards, this cart is accelerating towards the right. So it starts at rest, it moves, then it starts to move a little faster, and then a little faster, then a little faster, because it's accelerating towards the right. And because it's accelerating towards the right, that's why when the ball is shot up, it falls behind the cart, because this ball is not accelerating in the X direction. The ball is not accelerating in the X direction. So it just goes up, and then while the cart is moving faster and faster, it moves ahead of the ball such that the ball falls behind it. All right, so another problem that's in your mastering physics that I want to discuss real quickly is, let's see here. So another one I want to discuss real quickly is the one where the man basically goes on top of a ladder. It's a ladder. He's standing up here and he throws a ball that way, and he just drops a ball straight downwards. So one ball just falls straight down, another ball goes like this. All right. So then the question is, which ball has the greatest speed at the moment of impact? Okay. Well, we know this ball, we know both of these balls basically going to hit the ground at the same time, right? Because they're both being dropped from the same height. Now, notice that this ball only has speed in one direction when it's falling down. So it only has basically this downward speed that's increasing the further and further it goes down. Whereas this ball has not just the downward speed, but also this horizontal speed that he threw to the right. So it has this speed to the right, and it also has the speed downwards. So that when this ball hits the bottom, it has two speeds that it's hitting the ground with, the speed to the right and the speed downwards, versus this ball only has that one speed downwards. So hence, this ball is going to hit the ground with a greater impact just because it has both of those speeds. Okay, so let's see here. So another problem I want to discuss is one that says to begin your wingsuit flight, you step off of a cliff. So you're on some cliff and you have some wing flight suit like this. You step off of the cliff and it says, why are you then momentarily weightless? And then it says, at this point, is gravity acting on you? So you just step over the edge. So basically, when you first step over the edge, none of the wind has caught under your glider yet, right? And so since none of the wind is pushing you upwards, let's see. So none of the wind is pushing you upwards just yet because you just stepped off. So for that one moment, you're gonna feel weightless until you start to fall downwards. So yes, gravity is still in effect. Gravity is still in effect. Yes, gravity's still in effect. But you feel weightless for just that one moment because none of the air is pushing you up just yet. And so that's why you feel weightless for that one moment. Until then, you just start to fall, then you're falling, then air will start to push you up, and then you'll kind of glide through the air. Right? So let's see. Boom, boom, boom. And then another problem I want to talk about involves potential and kinetic energy. So potential and kinetic energy, where potential energy is basically associated with the ability for movement, or you have the potential to begin movement. And kinetic energy is basically just energy related to motion. So for example, potential energy would be anything. Let's say we have a hill here and a ball is just resting here on this hill, and this hill has some height upwards, right? Well, we would say since this ball is not rolling, it has zero kinetic energy, because kinetic energy is related to motion. Remember, kinetic means motion. But it has some potential energy because it has the potential basically to roll down here. So it has some potential energy, but it has no kinetic energy. So then once this ball begins rolling, so if I were to like make a chart here, so a chart, let me see if I can draw this right. Let me actually use a different color. So let's say this was a chart for potential and kinetic energy. So red indicating up here at the top, it has some potential energy, right? But it has no kinetic energy. And then down here at the bottom, right, so the ball's gonna roll and then continue to roll. It's gonna have basically no more potential energy, because all the potential energy has been converted now into kinetic energy. So this to indicate that it has some kinetic energy now, but no potential energy. And then as it's rolling down right here, as it's rolling down, it basically has, I would say, about half and half. Half and half. So basically, as this ball begins to roll down, it's picking up speed, so the kinetic energy is going up. But then as it goes down the hill or the ramp, then the potential energy the kinetic energy is going up. The potential energy here is actually going down. So at the top, it has all the potential energy, and as it goes downwards, potential energy decreases. Then also as it goes downwards, kinetic energy is increasing until it reaches the bottom. Then kinetic energy is going to be the amount of energy that it has, and then there will be no potential energy left over because now it's on the ground. And so basically this is going to relate to I think the last couple of problems, or maybe not the last couple, but it's going to relate to the problem of, say you're on a cliff here and they give you basically 3 scenarios. These 3 scenarios. With this one, you throw a ball. You throw a ball straight off the cliff this way. This one, you throw a ball kind of upwards. This one, you throw it downwards. And so we know each one of these is going to give some type of projectile motion. So this one's going to be like that. This one's going to be like that. And then this one's going to be like that, right? So since on each of these scenarios, we start at the same height, that means the potential energy initially is going to be the same for each. So potential energy, I'm going to use PE, is the same initially. So the potential energy is the same initially. So since the potential energy is the same initially, that means finally at the very end, the kinetic energy is going to be the same. So and it also says that the speed that you threw each of these balls is the same. So since the speed thrown is the same, since the speed thrown is the same, then kinetic energy is the same for each one of those. Because we know kinetic energy, or KE, is related to the speed. So the greater the speed, the greater the kinetic energy. But we know each one of these speeds were initially the same. So the kinetic energy is initially the same for each. And same goes for when each one of these hits the ground. Since they all begin with the same potential energy, then they must all end with the same kinetic energy. And then obviously we know basically this one in the middle is going to have the longest flight time. This one's going to have the shortest because it's being thrown straight down. And then this one's going to be somewhere in between. Alrighty, so that's about it for this video. So lab number 4 is going to be over projectile motion. So lab 4 is over projectile motion. All right. So lab 4 is over projectile motion. I've kind of already discussed a little bit of projectile motion in this video. Of course, I just kind of brushed over it a little bit. The chapter will have more details on projectile motion that may make the lab make a little bit more sense. I will also be posting a video of the review probably sometime tomorrow. And let's see what else. Yeah, and that's pretty much it. Good luck with the homework, good luck with the lab. I know this class is moving pretty fast. Again, because it is a summer class, if you don't understand some of these concepts right away, don't feel bad about it again. This stuff is, very advanced, and it takes some time to kind of get used to. And I didn't even go into all the detail on a lot of these subjects. The book has a little bit more detail, but even then, it still may be hard to understand. But just keep at it, and good luck. See you next time.